Hello, my name is Santiago Rincon, and today I'll be talking about Chapter 8.1, testing the difference between means, large independent samples. So first, we'll have to know what an independent sample is. An independent sample is a sample selected from one population that is not related to the sample selected from the second population. And a dependent sample is a sample that each member of one sample corresponds to the member of another sample. So today I'll be using this example. It's a two-sample t-test for difference between means. It states that the result of a state mathematics test for a random sample of students taught by two different teachers at the same school are shown at the left. Here's our data. Can you conclude that there's a difference in the mean mathematics test scores for the students of two teachers? Use alpha equals 0.1 and assume the population's normal distributed and the population variances are not equal. Okay, so first we need our claim. So our claim is that there's a difference in mean mathematics test scores for the students of two teachers. Okay, and now we have to state the null and the alternative hypothesis. So the null hypothesis is that the mean of 1 is equal to the mean of 2, and that alternative hypothesis is that the mean of 1 is not equal to the mean of 2. This is our claim, right? Okay, so now we have to find the degrees of freedom and the critical value and the rejection area. Okay, so the degrees of freedom are our lowest. The smallest sample size is 8. So 8 minus 1 is equal to 7. This is our degrees of freedom that we're going to use. But since it's two-tailed and our alpha equals 0.10, the critical value, if you look at our chart, is 1.895, negative 1.895, and positive 0.815. And this is a rejection region. T is less than 1.895, negative, and T is greater than 1.895. Okay, so now we have to find our standard error. Okay, so to find our standard error, we have to use this formula. X bar 1 minus X bar 2, which is equal to the square root of S1 squared over N1 plus over N2, right? Which is a square root of our values from before. So S1 is 39.7 squared over N1 is 8 plus S2 is 24.5 squared over N2 is 18. This is approximately equal to 15.1776. Okay, so now we have to find this standardized test statistic And the formula is t equals x bar 1 minus x bar 2, parentheses, minus the mean of 1 minus the mean of 2 over S, our standard error, which you found above. So then it's equal to 473 minus 459, which are x bar 1 minus x bar 2. Since we don't know our mean, we'll put 0 over the 15.1776, and we find it to be approximately 0.922. Okay. So now if we look to the rejection region from before, it was less than negative 1.89 and greater than 1.89. So let me draw it. The bell curve. Like this, negative 1.895. 1.895. So our value lies approximately in the middle of these, around here. So this is 0.922. Okay. Right? Okay. So now we have to support or fail to reject or fail to reject the claim. So since this graph shows us that the location of the rejection region and the standardized test statistics t, because it's not in the rejection region, it's outside of it, we fail to reject. So I fail to reject the null hypothesis. And how do we interpret this? Okay, so there's not enough evidence at the 10% level of significance, which is our alpha, to support the claim that the mean mathematics 4 test scores for the students of the two teachers are different. All right, thank you guys, and see you next time.